We have already studied exponential growth and decay, but using only the methods of pre-calculus. Now that we have learned about the differential equations in calculus, we can re-examine growth and decay in a whole new way. Hi, my name is Tom Atwater, and we need to start our examination with what are called separable differential equations. So let's take a look. A differential equation of the form dy dx equals f of y times g of x is called separable. We separate the variables by writing it in the form 1 over f of y dy equals g of x dx. The solution is found by anti-differentiating each side with respect to its thusly isolated variable. So let's look at an example where we can apply this. Let's take and solve for y in the equation dy dx equals x squared times y squared when x is equal to 1, then y is equal to 1. Okay, so the first thing we need to do is separate this out. And so we have y to the negative 2 dy equals x squared dx. And so what we need to do is to integrate both sides of this. So I'm simply going to put the integral in front of each one. And now what we have is negative y to the minus 1 is equal to x cubed over 3 plus c. And even though on both of these we would have technically a plus c, we can combine whatever that constant is just to be on one side, and hence I've put it on the side with the x's, although it really makes no difference. So now the next step is we know that when x is equal to 1, y is equal to 1, and that would allow us to solve for c. So we plug in negative 1 to the negative 1 equals 1 cubed over 3 plus c. And that will give us an answer for c of negative 4/3. So we can plug that back in, and what we now have is negative y to the negative 1 is equal to x cubed over 3 minus 4/3. Let's simplify that a little bit. What we can do is combine the right-hand side, make that x cubed minus 4 all over 3, and then recognize on this side we have negative y raised to the negative 1, which means that it's negative 1 over y. And therefore, we can take the reciprocal of both sides as well as bring the negative sign over to the right-hand side, and we would get an answer for y, which is this. Y will be equal to, y is equal to negative, the reciprocal, so it would be 3 over x cubed minus 4. And I suppose we could take it one more step and say that this would be equal to 3 over 4 minus x cubed. Now, the thing is this. Remember when we talked about continuous functions? Well, this particular function has a discontinuity point. We are looking at the point 1, 1, which means our domain, and let me just get some space for this, our domain is going to have to be that section that contains the 1, 1. And that section starts at negative infinity and then goes up through, if you take the denominator of this and set it equal to 0 and solve it, you will see that x is equal to the cube root of 4. And so we need to put that inside, and that gives us the domain on which this function is continuous, which includes the point 1, comma 1. All right, well, that's a separable differential equation. So now we'll begin our exploration of growth and decay. We've seen enough growth and decay models to know that the growth or decay is proportional to the amount present. That is, the more bacteria in the dish, the faster it grows. Let's look at the differential equation that describes this growth. Here we go. If y changes at a rate proportional to the amount present, then the equation is dy dt equals k times y, where k is a positive number, represents growth, and if k is a negative number, then it represents decay. The number k is called the rate constant of the equation. Let's actually take that equation, dy dt equals ky, and let's solve that differential equation. So the way we're going to do that is, of course, to separate them out. So what we have is 1 over y dy equals k times dt. Then what we're going to do is integrate both sides. So I'll just stick the integrals in there. And then on this side, we're going to get the natural log of the absolute value of y. And on the right-hand side, we're going to simply get k as a constant, remember. So we're going to get kt plus the constant. Then what we can do is take this equation and raise both sides to, or raise e, the base of e, to both sides of this. In other words, e to the log of the absolute value of y, and e raised to that entire sum, kt plus c. Why do we do that? Because on the left-hand side, e raised to the natural log of the absolute value of y is just the absolute value of y. So we get the absolute value of y is equal to. And then I can do this thing where when you are adding the two exponents, that comes from the product of two exponential expressions. In other words, e raised to the c times e raised to the kt. And now maybe you can see it more clearly that when we multiply those, we add the c plus the kt. All right, next, what we want to do is simply put that y is going to equal plus or minus, and then I'm going to change this to just be a different constant a, and leave e to the kt as it is. And so that would be the solution to our differential equation dy dt equals k times y. This formula we'll work more with throughout the remainder of today. Let's look now at what's called the law of exponential change. If y changes at a rate proportional to the amount present, dy dt is equal to ky. And y equals y sub 0 when t equals 0. Then y is equal to y sub 0 times e to the kt. The constant k is the growth constant if k is positive, or it's the decay constant if k is negative. Let's revisit the formula for compound interest. Compound interest, the formula is a of t is equal to a naught, or a sub 0, times the quantity 1 plus r divided by k, all raised to the kt, where a naught, or a sub 0, is the amount invested originally, r is the interest rate, and k is the number of times the interest is added, or compounded, to the account per year. This formula that we looked at, we then went into compound interest which is compounded continuously. So let's look at this formula. If interest is compounded continuously, then the differential equation is dA dt equals R times A. The initial condition is A of 0 equals A naught, or A sub 0. The amount of money after t years then is A of t equals A naught times e to the RT, where R is the continuous interest rate. Okay, so that was a bunch of formulas we looked at right in a row. So let's do an example so we can see those in action. Let's take the problem, find the amount of time required for a $2,000 investment to double if the interest rate is 4.75%, 4.75%, and it's compounded first monthly and then next continuously. Okay, so the amount invested is $2,000 at 4.75%, and it's monthly. So this time the formula, of course, is A of t equals the original amount, 2,000, times 1 plus the interest rate, written as a decimal, over the number of times that it's compounded, 12, raised to the number of times it's compounded times t. And the amount that we're interested in is that it doubles. So therefore, I can simply erase the A of t and say, okay, what we're really looking for here is when it is 4,000. Okay, so now let's solve this. First of all, we can divide both sides by 2,000, which gives me a 2 here. Now, we're trying to solve for t, which is up in the exponent, and therefore we want to take the log of both sides, because if we take the natural log of 2, and then we take the natural log of 1 plus 0.0475 over 12 raised to the 12t, we can now bring the 12t down in front. And what we'll have is log 2 equals 12t, the natural log of 1 plus 0.0475 over 12. And then to solve for t, all we need to do is divide both sides by 12 log of 1 plus 0.0475 divided by 12. So in other words, t is going to be equal to the natural log of 2 divided by 12 times the natural log of 1 plus 0.0475 divided by 12. And of course, plug that into your calculator, and that works out to 14.62 years. Okay, so it takes a little over 14 and a half years to double that $2,000 with the interest rate of 4.75% when it's compounded monthly. Well, now let's take a look at what happens when you compound it continuously. When we compound it continuously, the formula we're going to use is that the amount, A of t, is going to be the initial amount, which is 2,000, and that's going to be multiplied times e raised to the interest rate times t. Again, we're looking at wanting this to double, so let me erase this and put in my 4,000. Of course, I can divide both sides by the 2,000, and I get my 2. And now I have the natural log of 2 equals the natural log of e to the 0.0475t. Now, this time what happens is, remember, the natural log is log base e. But if I have the natural log of e to the some power, that is just the power. In other words, I get log 2 is equal to 0.0475 t. And that means my t would be equal to the log of 2 divided by 0.0475. And when you plug that into the calculator, what it works out to be is 14.59 years, which to me is pretty amazing that compounding it by the month versus compounding it continuously, and I only have just about 3/100ths of a year that I save by doing that in terms of doubling my interest, doubling my initial investment, doesn't seem like a whole lot. So what we learned from this is compounding continuously is not that much different than compounding every single month. Okay, well, let's take and work another type of an example that has to do with radioactive decay. So the formula for radioactive decay is y equals y naught e to the minus kt, where k is a positive number, which means I want to point out then that we're saying k is positive, and that's why we need the negative sign in this formula. And y naught is the amount present at time 0, and y is the amount present at time t. Now remember, what radioactive decay is that the nucleus of the material is emitting energy in the form, emitting some form of its mass in the form of energy, and then it's reforming into a different element. And those elements whose atoms spontaneously go through this process are called radioactive elements. So let's look at an example of what's called half-life. The half-life of a radioactive substance is the time required for half of the radioactive nuclei present in the sample to decay. So let's take the time and actually figure out, what is the half-life then? How do we calculate that? Well, we start with our formula, which is, of course, y equals y naught e to the minus kt. And in this particular formula, we want half of the substance to decay. In other words, let me go one more screen. What we're looking at is we want 1/2 of y naught. And we want to figure out how long that takes for the substance to decay. So what we do now, of course, these two can cancel each other out. We can take the log of both sides, and this is going to be the natural log of 1/2, which, remember, is minus the log of 2. And on the other side, when we take the natural log of e raised to the minus kt, that's just equal to minus kt. And therefore, when we solve for t, we have this and this that we're working with. What we have is t is equal to the natural log of 2 divided by k. And what this tells us is, of course, the formula for half-life, which is the log of 2 divided by k, which is the decay constant, which means that the half-life is only dependent on the decay constant. That's all that matters to determine the half-life. Now, let's look at a formula for modeling growth with other bases besides E. The growth equation for bases other than E. The formula for growth using a base other than E is given by y equals y naught b raised to the ht, where b is the base and h is a rate constant which is related to K by the equation K equals H times the natural log of B. So if you were to have growth rates with bases other than E, this is the formula that you would use. But right now what we're going to do is turn our attention to Newton's law of cooling. Newton's law of cooling, the formula for the rate of cooling or warming of an object in its surroundings is T minus T sub s, standing for the equals the quantity T naught minus T sub s times e to the minus kt, where T is the temperature at time t, that is capital T is the temperature at time t, T naught is the temperature at time 0, T sub s is the surrounding temperature, and K is the rate constant. Let's try an example of where we can apply Newton's law of cooling. Let's take the example that a hard-boiled egg at 98 degrees centigrade is put in a pan under running 18 degrees centigrade water to cool. After 5 minutes, the egg's temperature is found to be 38 degrees Celsius. How much longer will it take the egg to reach 20 degrees? All right, well, I've written down some of the more pertinent information on the next slide. We have a starting temperature of 98 degrees Celsius for the egg. The surrounding temperature, which is the temperature of the water that's running and covering the egg, is 18 degrees. We know that the temperature goes down to 38 after 5 minutes. So we're asked to find T, that is the time that it would take to go down to 20 degrees. However, before we do that, we have to find the K, the constant here. So let's plug some numbers in. We have T minus the surrounding temperature, 18, equals the starting temperature, 98, minus the surrounding temperature, the 18 degrees. E raised to the minus KT. Okay then, so what we have is, of course, this is 80, and we're told that when T is equal to 5 minutes, that the temperature was 38. So we plug those two numbers in, and that will allow us to solve for K. So what that looks like is 38 minus 18 equals 80 e to the minus k times 5. Okay, so here, of course, is 20. We divide both sides by 80, and that would be 1/4 on the left-hand side. I'm going to take the log of both sides, so the natural log of 1/4, which, remember, we can say is the negative natural log of 4. And when I take the natural log of this side, then the base cancels out with the e, and we get negative 5k. So now to find k, I simply divide both sides by negative 5, which gives me log of 1/4 divided by 5. So that was the first part of this problem, is just calculating the value of k. And so now what I have is, on my next slide, I have the equation with k plugged in. And I have the information that we're interested in finding. So the equation now is t equals 18 plus 80 e to the minus 1/5 log of 4 times t. And we want to find t when the time t, when the capital T temperature is 20. So we plug in 20 equals 18 plus 80 e raised to the minus 1/5 log 4 times our unknown t. And that's what we want to solve for. So again, we subtract 18 over here, and we're left with 2. We divide both sides by 80, which is going to actually give me 1/40th on this side. So I do the log of 1/40th, which is minus the log of 40. And that's going to equal, again, when I take the natural log of this, then I end up with just negative 1/5, the natural log of 4, all times t. So then my t is equal to 5 times the natural log of 40 divided by the natural log of 4. And when I work that out, that's going to be 13.3 minutes. And what that means is that it's going to take an additional 8.3 minutes to cool from the temperature of 38 down to 20 degrees. All right. Well, now it's time for you to try a problem just like that. So here's the problem that I would like you to do. Suppose that a cup of soup cooled from 90 degrees centigrade to 60 degrees centigrade in 10 minutes in a room whose temperature was 20 degrees. Use Newton's law of cooling to answer the following. How much longer would it take the soup to cool to 35 degrees Celsius? Pause the video while you work on this problem, and when you are finished, restart the video to check your solution. Okay, I've written down on the next slide the important pieces of information. And so let's plug those numbers in and get going. So we have T minus the surrounding temperature is 20 equals the initial temperature, which is 90, minus the surrounding temperature, 20. And that's going to be times e to the minus kt. So if we maneuver a little bit there, what we have is to plug in that on a time of 10 minutes, the temperature cooled down to 60 degrees. So what I'm going to have is 60 minus 20 equals 70 e to the minus k times 10. And of course, 60 minus 20 gives me 40. 40 divided by 70 is 4/7. So I'm going to have the natural log of 4/7 equals, and again, when I take the log of this side, I just get the exponent brought down, so it's minus 10k. So therefore, k is going to be equal to the 1/10, the log of 4/7. And actually, I'm sorry, I should put my minus sign in front of that. So that's my value of k, and that's just the first part of solving this problem. We now need to take that k and plug it back in to our equation. So I've done that on my next slide, so let's take a look at that. Our equation then is t equals 20 plus 70 e to the 1/10 log of 4/7 t. We want to find the time t when the temperature goes down to 35 degrees. So 35 equals 20 plus 70 e raised to the 1/10 natural log 4/7 times t. So subtract 20 from both sides, and this becomes 15. Divide both sides by 70, and we have 15/70ths, which reduces to 3/14. So I have the natural log of 3/14 is going to equal, again, when I take the natural log of this side, I simply bring down the exponent, 1/10 the log of 4/7 times t. So t will be equal to 10 times the log of 3/14 divided by the log of 4/7. And when you plug all of that into your calculator, you'll come up with 27.53 minutes. And that means, because the original time was 10 minutes, that we need an additional 17.53 minutes to cool this egg down to a temperature of 35 degrees. Okay, well, that's a great use of Newton's law of cooling and a great session for today. So in today's session, we looked at Newton's law of cooling, and we revisited growth and decay, including compound interest and half-life. Be sure to work the exercises that your teacher assigns, and we'll see you next time.